Hi everyone. Today we're going to look at how to apply transform to solve differential equation. So this is where the Laplace transform take place to solve first orders or second order or even third order differential equation, especially your ordinary differential equation. Okay, so let's look at how the definition of this transform of derivative looks like. Okay, if we have a function f prime t that is continuous for t greater or equals than 0, then the Laplace of f prime t is given by the definition of Laplace transform exponent negative st. Now, this is my ft here, which is f prime t dt. Okay, obviously to solve this, you need to use integration by part. Okay, I would say this to be your u and this term to be your dv. Okay, so let's work the uv first. If u equals to exponent negative st, du dt is given by negative s exponent negative st. Okay, if dv equals to f prime t, taking the integral of f prime gives you ft. Okay, now you can apply the formula, the uv integration by part formula. Now let's change this limit 0 to infinity to limit as b approach infinity from 0 to b exponent negative st f prime t dt. Okay, by the integration by part, limit b approach infinity u v limit from 0 to b minus integral from 0 to b v. Now what is du? Du is this, negative s exponent negative st dt. Okay, so this is the whole thing here. Okay, so now we can just apply the integral here, the limit here, b approach infinity. So I have exponent negative sb function of b minus exponent negative s of 0 f of 0. I just did the first part here, this part here, which gets this whole thing, and then minus, let's take out, plus limit b approach infinity. Okay, integral of this one. Now we have to integrate with respect to t. So let's write it as, take out the t, the s, of 0 to b, ft exponent negative st dt. Okay, so now we're left with this. Here, what is this? If you look at this, this is this whole thing here. Limit b approaching infinity 0 to b is this thing. The definition. The definition, the Laplace. If you recall, the definition of Laplace transform. What is the definition of Laplace transform? So the Laplace of ft is given by limit from 0 to infinity exponent negative ft dt, right? Then obviously if you take the limit here this will be limit b approach infinity 0 to b exponent negative f st f t dt. So this whole thing is equals to this. So I can say this term here together with the limit is equals to the Laplace of ft. Okay, so now we're going to do is simplify this term here. Okay, continuing we have, so what we want to find the Laplace of f prime t is given as, okay, this term here. So when b approach infinity, this term tends to 0. Okay, and then e to the power of 0 is 1. So I have negative f(o), negative f of 0, okay, and then plus s of Laplace transform ft. Okay, so I hope you're with me. So what is this? I can write this as S Laplace of small ft is my big Fs minus f0. Okay, so this is the definition of Laplace transform of f prime t. Okay, you can also show, okay, I'll let you work this out. You can also show that the Laplace transform of the second derivative is given by s squared f of s, big F, minus s of f(o) minus f prime 0. Okay, you can show this as your homework. And similarly, we can also have the third derivative and so on. Okay, the third derivative is given by s3, big F of s, minus s squared f of 0 minus s f prime 0 minus f double prime 0. Okay, so in general, the definition of the Laplace transform of the derivative, okay, in general, the Laplace transform of f for n derivative is given by s of n fs minus s n minus 1 f of 0 minus s n minus 2 f prime 0 plus negative f n minus 1 0. Okay, dot here, dot. Okay, so this is the general definition of Laplace transform of the derivative. Okay, now why this is important? So we can solve Laplace problem, Laplace transform, to solve initial value problem. These are the application of Laplace transform. Okay, so that's why we want to learn the basic way, some of the properties of Laplace transform before you use that to solve initial value problem. Okay, so the idea is, okay, so we have the equation. Okay, we're given an equation. So what do we do with this equation? We transform. Take the Laplace transform of the equation. Okay, that's my next step. And then the last step, we solve the transform equation. equation, which means that you take the Laplace inverse of the transform equation. So there are 3 steps that you need to take off, okay? So given an equation, we take the Laplace transform, and then to solve means take the inverse Laplace transform. Okay, so my next video, I will be giving you some example on how to solve this Laplace transform of a derivative. But to understand this, first of all, you need to know how to take the inverse. Since I have some time here, let's look at inverse Laplace transform. Okay, this is the inverse Laplace transform. So the table of inverse Laplace transform is the opposite table of the Laplace transform. Okay, so for instance, we have fs, and then the Laplace inverse of this fs is your ft. Okay, so if my ft is 1, the inverse is 1 over s. S must be greater than 0. Okay, similarly, the Laplace transform of Tn is n factorial over Sn plus 1, or the inverse Laplace transform of this, get Tn. If the Laplace transform of exponent t is 1 over s minus a, the inverse of 1 over s minus a will give you exponent at. Similarly, the Laplace transform of kt is given as k over s squared plus k squared. Okay, this means that the inverse of k over s squared plus k squared will give you sine kt. And then for cos, the Laplace transform of cos, you know, is given by s over s squared plus k squared. So the inverse of this will give you cos. And then we have another one, the combination of cos and sine, such as exponent at sine kt. The inverse is given by, the Laplace transform is given by s minus a squared plus k squared. Okay, and then we have with the cos, exponent with the cos, which is given by s minus a over s minus a squared plus k squared. The inverse of this is exponent at cos kt. And lastly, we have the Laplace transform of Tn exponent at, which is given by n factorial over s minus a n plus 1. Okay, so if we know this, you can take the Laplace transform of any function. Okay, I'll show you one. Give you one example. I don't have much time here, but I'll give you one. So find the inverse Laplace transform of 1 over S4. Okay, so from the table we know that this one. This is the table. The Laplace of n factorial, so we want to look at this one here. They look the same. So how you write it? So from the table we know that the Laplace inverse of n factorial over Sn plus 1 is given by Tn. So we know that my n is 4. Okay, my n plus 1 is 4. This one. So what we have here, when n is 3, I have 3 factorial over S3 plus 1. So what is this? 1 over S4 is equals to 3 factorial over S to the power of 3 plus 1. okay, which is equals to get this 1 over S4, this is what we want. So we have to divide by 3 factorial, multiply with 3 factorial over S4. Okay, now why we want to divide by 3 factorial? Because if I cancel these terms out, that will give me 1 over S to the power 4. So, the inverse Laplace of 1 over S4 is given by the inverse Laplace transform of 1 over 3 factorial multiplied with 3 factorial over S4. Okay, 1 over 3 factorial, you can take it out. So 1 over 3 factorial is 6. So I have 1 over 6. Now the Laplace transform of 3 factorial over S. Now n is 3 here, so I can actually write like this. Okay, now what is this? By the definition, when n is 3, okay, so you have t to the power of t. So my solution is 1 over 6 t to the power 3, because this one comes from here. Okay, so this is the inverse transform of 1 over S4. Okay, it's not that complicated. Maybe we can look at one more example here. How about one challenge example? Okay, so find the inverse transform of 1 over S squared plus 49. Okay, if I have not explained to you, the symbol of inverse transform is given by L, Laplace inverse. Okay, it means inverse. Okay, now how do you find the inverse of this? So let's look at the table. The closest table that we can see from the Laplace transform is this one, maybe. Okay, oh yeah. K over S squared plus K squared, okay, is given by sine KT. This is the closest form of transform that we can use. So let's write it down, what we have here. So from the table, Laplace transform table, we know that the inverse transform of K over S squared plus K squared is given by sine KT. Right, so I can write this. K is, this is 7. Okay, if I take K equals to 7, so what do I have? I have 1 over S squared plus 7 squared equals to, now I have to cancel out. I have 1 here, okay, so it means that I need 1 over 7 over S squared plus 7 squared. Are you with me? So that if I cancel the 7 out, I'll get 1 over S squared plus 7 squared. Okay, so now if you take the Laplace transform, or the inverse transform, taking the inverse transform of 1 over S squared plus 7 squared, that gives me 1 over 7, the inverse Laplace transform of 7 over S squared plus 7 squared. Okay, that gives you 1 over 7. Now what is this? When K is 7, I have sine 7t. Okay, that's not too bad, right? That's not too bad. Okay, let's look at one more example on Laplace transform. Okay, so let's look at find the Laplace transform, find the inverse transform of 2s plus 3 over s squared plus 6. This is different. You cannot find this form on the Laplace table. Okay, you cannot find this form. But we need to simplify. Okay, so let's write like this. So the Laplace transform of 2s plus 3 over s squared plus 6 can be written as, okay, the Laplace inverse. Now I want to write this as 2s over s squared plus 6 plus 3 over s squared plus 6. Okay, this is the Laplace from the table. Okay, so what we do here now, we need to simplify. So you have to agree with me. These are the same form, right? So I can combine as this. Okay, once we get this form, now I can separate by the inverse Laplace transform property, where I can write this as 2s over s squared plus 6 plus the Laplace inverse of 3 over s squared plus 6. Okay, now what we do here, so what does this form look like? I can say one look as cos. One has the sine Laplace transform term here. So let's look at our Laplace table. So we can have these two forms. Okay, you have to print it out or paste it somewhere to make it handy. So we know that k over the Laplace inverse of k over s squared plus k squared give you sine, and the Laplace inverse of s over s squared plus k squared give you cos t. So we want to use these two definition of the inverse to our solution here. Okay, so what we do here, so I can take the 2 out, and then that gives me inverse of s over s squared plus square root 6 squared. Okay, and then this one, take the 3 out, Laplace inverse of 1 over s squared plus square root 6 squared. Okay, so now by the table, we know that this one must be s over s squared plus k squared. So my k is square root 6. So that gives me 2 cos k is square root 60. Okay, this is good. Now what about this one? This, for the sine, from the table, I have k squared over s squared plus k squared. So I need square root 6 here. But at the same time, I need to divide by square root 6. So that will give me, let me just simplify it first. Okay, I hope you are looking at the pattern right now. So I need to divide by square root 6 because when I cancel this out, it gets back the same term here. Okay, so now you are almost to your solution, where this is sine square root 60. See, this is how you solve a Laplace transform involving problems that you don't find it directly on the Laplace transform table. Okay, and there are some problem that you need to use partial fraction to solve it. Okay, I can show you one example on using partial fraction form. So the Laplace inverse of 1 over s squared plus s minus 20. Okay, so before we take the Laplace inverse, you need to write this in the form of partial fraction. So I can factor this out as s plus 5, s minus 4. Now by the partial fraction, I have a over s plus 5 plus b over s minus 4. Okay, so simplifying what we have here, 1, find a and b, okay? So a s minus 4 plus b s plus 5. So if we take s equals to 4, I have b equals to 1 over 9. If I take s equals to minus 5, I have a equals to negative 1 over 9. Okay, so now we can have this form. 1 over s squared plus s minus 20 equals to a over, which is negative 1 over 9 over s plus 5 plus b over s minus 4. b is 1 over 9 over s minus 4. Okay, so now you take the Laplace inverse of 1 over s squared plus s minus 20, which means taking the inverse of Laplace inverse of negative 1 over 9 s plus 5 plus the Laplace inverse of 1 over 9 over s minus 4. Okay, so now what can we say? So from the table, okay, from the Laplace table, what do we know? We know that the Laplace transform of exponent at is given by 1 over s minus a, which means the Laplace inverse of 1 over s minus a is given as exponent at. So I'm going to use this two property here, this two definition. Okay, so the Laplace inverse of 1 over s squared plus s minus 20 is given by, okay, so to get a here, so my a is 5, right? So I have to divide by 1 over 9. I have to cancel these terms out. So how do I do that? So I just take out this negative 1 over 9, Laplace inverse of 1 over s plus 5 plus 1 over 9 Laplace inverse of 1 over s minus 4. Okay, so what is this? So a is negative 5 here. So I have 1 over 9 exponent negative 5t plus 1 over 9. In this case, a is 4. There you go. That's how you find Laplace. So let me give you homework for today. So find the inverse Laplace transform of 1 over s, not this one, we already done this one, s squared plus 6s plus 9 over s minus 1, s minus 2, s plus 4. Okay, and then you can do another one. So the Laplace inverse of 3s minus 2 over s squared plus 4. Okay, so work this out and I will see you in my next video. That's all for today. Bye.